At this point, we have a couple more quick ways to tell that certain functions are continuous. The first thing is we're going to be looking at inverse functions. And so Theorem 4 from the section tells us that if our function f is continuous on some interval I with range r, and if, let me make that r a little bit better. If f is continuous on an interval I with range r, and if f inverse exists, then f inverse is also going to be continuous with domain R. And so a quick little justification for that basically has to do, I'll just do a little picture demonstration here. So let's say that this is the graph of our function here. This is clearly going to be continuous, and I think we can agree that the inverse exists. And so the thing that we can do in order to plot the inverse, plotting the inverse just involves reflecting our function over the line, y is equal to x. And so it's going to look something like this. And so we see that this is continuous, and we also see that just from the picture that this is continuous. Here, the range is R, and that corresponds to the domain being R. So, so now we know that inverse functions exist. And so, from before, we know that there's lots of functions that we already know are continuous, and so this gives us even more functions that are continuous. So, for example, because we know trig functions are continuous, now we know that inverse trig functions are continuous on their domains. So inverse sine of x, for example. We know that, let's see, nth roots are continuous because we know that the power function x to the n is going to be continuous, so x to the 1 over n is going to be continuous. So lots of things that we get very quickly for free here. One more thing to do here is going to be composition. So as it turns out, if we compose one continuous function with another continuous function, the output's going to be a continuous function as long as everything's defined, as long as we take care of all the special things that we would need to take care of. So Theorem 5 says if g is continuous at x is equal to c, and if f is continuous at x is equal to g of c, then f of g of x is continuous at x is equal to c. So we compose one continuous function with another continuous function. So x of c, so g of c is where we're evaluating f at here. So f of g of x is going to be continuous. So just a couple of quick examples here of functions that are going to be continuous. X squared plus 9 to the 1/3. X squared plus 9 is continuous. Taking a cube root is continuous, so this is continuous on its domain. If we were to, another one would be cosine of 1 over x is continuous. Of course, it's not continuous for when x equals 0, but other than that, it will be continuous. 1 over x is continuous. Cosine is continuous, so this is also continuous. So we can see that There's lots and lots of ways that we can combine functions together that will allow us to quickly conclude that they are continuous.